Relative angular velocity discussion is continuing. Angular velocity of particle 2 with respect to particle 1. Angular velocity of 2 with respect to 1 is defined as or given as the velocity of 2 with respect to 1, its component perpendicular to the line joining these two particles or points. That is V21. Open. The distance of separation when you stand on this particle 1, this particle seems to move with the velocity V21 in this direction. When you stand on this particle 2, the particle 1 seems to move in opposite direction. Perpendicular to the line joining them. This is the perpendicular component of the velocity of 2, velocity of 1 with respect to 2. Velocity of 1 with respect to 2. This is the perpendicular component of velocity of 2 with respect to 1. So we can say that one is turning around 2 with angular velocity omega 1 2, in whose sense in clockwise sense or in. Here 2 is turning around 1, in whose sense in clockwise sense with an angular velocity omega 1 2 or omega, that is omega 2 1. With a clockwise sense, with a clockwise sense. Magnitude omega 21 equal to V21 its perpendicular component by L, omega 12 equal to V12 perpendicular by L. This is the concept. Since V21 perpendicular is equal to V12 perpendicular, magnitude wise omega 12 and their sense of turning are same, then we can conclude that omega 12 is equal to omega 21. These two angular velocity vectors must be equal in magnitude, so also direction. So angular velocity of 1 with respect to 2 is exactly equal to angular velocity of 2 with respect to 1. This is the idea. Both magnitude and direction, the relative angular velocity of 1 with respect to 2 is exactly equal to 2 with respect to 1, whereas velocity of 1 with respect to 2 is equal to minus the velocity of 2 with respect to 1. The relative velocities in linear case, they are equal and opposite. But in angular case, they are exactly equal. That's a great concept. Let me emphasize on this fact now. Take these two particles, same example. This particle velocity is v1, this particle velocity is v2. You stand on the particle 1. Particle 2 seems to move in whose direction with what velocity? Let us calculate. When you stand on 1, particle 1, you can observe the velocity of particle 2, that is called velocity of 2 with respect to 1. When you stand on particle 2, you can observe the velocity of 1 with respect to 2. V12. When you are standing on particle 1, you are observing velocity of the particle 2 with respect to 1, because you are fixed with the particle 1, and V21 is equal to V2 minus V1 according to Galilean transformation of velocity. So subtract this vector from this vector, subtract V1 from V2. V2 minus V1. So you draw minus V1 here. This is V1, this is minus V1. And this is V2. This is V2. This is V1, this is minus V1. This is the line joining. When you add these two vectors, V2 minus V1 is nothing but V2 plus minus V1. So these two vectors V2 and minus V1 you add. If you add it by a parallelogram law of vectors, you are getting V2 minus V1 vector. And that's nothing but V2, 1. This is the velocity of 2 with respect to 1. Similarly, velocity of 1 with respect to 2, you can calculate only when you stand on the particle 2, and you can say that this point 1 is moving with velocity v12. That's equal to v1 vector minus v2 vector. It goes without saying that v12 and v21, these two are equal in magnitude but oppositely directed. Equal in magnitude but oppositely directed. When you are standing here, you are observing the particle 2's velocity with respect to u, means with respect to 1, in this direction. When you are standing on particle 2, you are observing the particle 1's velocity with respect to u or with respect to 2. That is v12. v12 and v21 are equal in magnitude and oppositely directed. The linear relative velocities are equal and opposite. Relative velocities are equal in magnitude and oppositely directed. This is one of the great concepts. If you take the component of the relative velocity v12 or component of the relative velocity v21 along the line of separation, you are getting v21 perpendicular or you are getting v12 perpendicular. It is not perpendicular, it is parallel. When you take the perpendicular component, this gives us v12 perpendicular, and this is v21 perpendicular. The component of the relative velocity along the line of separation is called velocity of approach. When they move towards each other, this is called velocity of approach, or it may, in some other case, if you take the velocity in this way, they may depart, or we can call it velocity of separation. We are not interested in the relative velocity component along the line of separation now. We are interested in the component of the relative velocity perpendicular to the line of separation. That decides whether the particles turn with respect to each other or not. Let us now finalize the concepts. Whether you stand here at point 1, you can see that point 2 has some relative velocity component perpendicular to the line of separation. So, the point 2 is turning around you. Point 2 is turning around point 1 with an angular velocity called angular velocity of 2 with respect to 1. And if you stand on 2, there must be a component of the relative velocity of 1 with respect to 2, normal to or perpendicular to the line of separation, that is v12 perpendicular. We are not considering the component or the projection or the part of the relative velocity between these two particles along the line of separation. We don't want that now. We are concerned with this perpendicular component of the relative velocity. Well, so when you say this particle turns in this sense, when you say from 1 particle 2 turns in this sense, and this sense is anticlockwise, this sense also is anticlockwise, but the sense of translation are totally opposite. v12 perpendicular is equal to minus v21 perpendicular, because v12 is equal to minus v21. And of course, v12 parallel along the line of separation will be equal to minus of v21 parallel. This signifies the fact that the linear relative velocities are equal in magnitude and oppositely directed. That part is very clear and diagrammatically also we have shown. Whereas the angular velocity of 1 with respect to 2 angular velocity of 1 with respect to 2 in an anticlockwise manner, because this 1 turns around 2 in this way, and angular velocity of 2 with respect to 1, this angular velocity of 1 with respect to 2 are having same direction, because this is anticlockwise, this is also anticlockwise. The direction part is anticlockwise. So, direction part of both the angular velocities are exactly equal. Now come to the magnitude part. The magnitude of omega 1 2 or omega 2 1 or and can be given as omega 1 2 is equal to omega 2 1 is equal to the relative velocity component, it's perpendicular. The component of the relative velocity along the perpendicular to the line of separation upon the distance of separation. Whereas their directions are equal. The magnitude of omega 1 2 and omega 2 1 can be given as V1 2 or V2 1 perpendicular by the distance of separation, and the directions are equal. Since these two conditions are satisfied, we can say that angular velocity of 1 with respect to 2, this vector is exactly equal to angular velocity of 2 with respect to 1, this vector. The angular relative velocities are equal in magnitude and equal in direction, and equal in magnitude and direction. That's the great idea. Omega 1 2 is exactly equal to omega 2 1 both magnitude wise and direction wise. Whereas linear velocity of 1 with respect to 2 is exactly equal to the linear velocity of 2 with respect to 1, but direction wise, in magnitude wise, but direction wise they are opposite. Omega 1 2 is exactly equal to omega 2 1, whereas V1 2 is equal and opposite to V2 1. After understanding the great concept of the relative angular velocity between 2 points or the 2 particles, they may not be rigidly connected. We can apply this concept in our rigid body kinematics to understand the angular velocity of the rigid body and to calculate that by this approach of relative angular velocity. Well, let us use the concept of relative angular velocity for the rigid body. You take a rigid body, take any 2 points inside the rigid body, point 1 and point 2. The line joining these 2 points has a distance L, this distance of separation. Well, you stand on any point, say 1, and you can see that point 2 moves in this way with respect to point 1 perpendicularly. Since L is constant quantity, dl by dt is 0. As you discussed, this quantity is the velocity of 1 with respect to 2 along the line of separation, or velocity of 2 with respect to 1 along the line of separation. That is what we can call the rate of change of distance of separation. That is equal to 0 because dl by dt is 0. So there is no relative velocity between any two points along the line of separation for a rigid body. Since V relative parallel is parallel along the line of separation, the relative velocity component is called parallel component. I take it parallel component 0. There is 0 relative velocity between any two points along the line of separation. There is no relative velocity or 0 relative velocity between any two points of a rigid body along their line of separation or along the line of separation, a line of their separation. Then V12 or V21 can be written as V21 perpendicular plus V21 parallel component. Since the parallel component will be equal to 0, V21 perpendicular can be written as V21. So relative velocity of 2 with respect to 1 is perpendicular to the line joining them. That's the idea. Hence, the relative velocity between any two points of a rigid body is perpendicular to the line joining them. When you look standing onto to point 1, point 1 will move in this way. Velocity of 1 with respect to 2 perpendicular, that's nothing but velocity of 1 with respect to 2. Velocity of 2 with respect to 1 perpendicular is none other than velocity of 2 with respect to 1 because there is no relative velocity along this line. Hence, any point seems to move perpendicular to the line joining to any other points. That's the idea. If you take this point here with respect to point 1, it may move. Suppose this 3 is V31. If you take a point here, this may move in this way, V41. These velocities are perpendicular to the line joining the respective points. So this observer can say that all points, they move with different velocities, but in the same sense. In the same sense, this point turns in this way, this point turns in this way, this point turns in this way, this point turns in this way with respect to point 1. That is the idea. And I will prove that the relative velocity between 1 and 4, 1 and 3, 1 and 5, 1 and 2, all the relative velocities are exactly equal in magnitude, source and direction because they are turning in the same sense. Let us take the rigid body. You stand here. You can see that suppose this point is O. Point A is moving in this way. Point B is moving in this way. Point C is moving in this way. Perpendicular to the line joining the respective points to O. This person can say that this person who is fixed or standing or is glued at this point O of the rigid body can say that all these points turn in the same sense if the rigid body moves with an angular velocity omega. So that omega BO is equal to VV by RB. Omega AO is equal to BAO by RAO. Omega CO is equal to BCO upon RCO. Now we have to prove that. To be proved, omega AO is equal to omega CO is equal to omega BO. It's quite clear. As you have discussed, any straight line drawn inside the rigid body, if the body is plane, rotating with omega, all the straight lines will rotate through same angle during any time interval dt. All the straight lines will rotate through same angle d theta during any time interval dt or del theta during any time interval del t. So all the straight lines will rotate in the same sense through same angle during a given time interval. In other words, we can say that the angular velocity of this straight line AO, this straight line CO, this straight line BO are equal to each other. That is given as angular velocity of the rigid body omega, which is the property of the rigid body that does not depend upon any outside point. Therefore, the relative angular velocity between any 2 points of a rigid body is the angular velocity of that rigid body. That is the concept. of angular velocity, definition by relative motion method. Angular velocity of the rigid body is nothing but angular velocity between any 2 points of the rigid body. That's the idea. Using this theory, I would like to solve the problem you have solved of the sliding rod or the bar under the 2 constraints by using the ground frame method. Same example, let us recast. Let us take 2 examples. This rod, this end moves with velocity v, this end moves with velocity v dash. So this 60 degree, such that if we equate the velocities along the rod, you will get same or equal quantities. So let it be theta. So this is 2 v cos theta and this is v cos 60 degree. Since the body is rigid along this line, there is no relative velocity. The latest discussion. 2 v cos theta is equal to v cos 60 degree. So cos theta is equal to v by 2 by 2. V will be getting cancelled. You are getting 1 by 4. So cos theta is 1 by 4. Now sin theta will be how much? 2 v sin theta, v sin 60 is equal to root 3 by 2 into v. Sin theta is equal to 1 minus cos square theta. Square root. Cos theta is 1 by 4, it will be 1 by 16. 1 minus 1 by 16 square root, that is equal to root 15 by 4. That is sin theta. Now we find omega of the rod. Omega of the rod is equal to omega of 1 with respect to 2 or omega of 2 with respect to 1. And that's equal to relative velocity of 1 with respect to 2 or 2 with respect to 1. There is no relative velocity along this direction, just we have to calculate the relative velocity along which direction? Perpendicular to the rod, that is equal to v relative perpendicular by L, or that is v relative by L, because there is no relative velocity along this rod, along this length of the rod between these 2 points. So this is 2v sin theta in positive direction minus, suppose this direction is positive, this direction is negative, this minus of minus this minus root 3 by 2 v. This is the relative velocity along this line of an L, because there is no relative velocity along this line. That's the idea. So you are getting minus plus, that is 2v sin theta, and sin theta value you have to substitute here. 2v into 15 by 4 plus root 3 by 2 v by L. So it will come v 15 by 2 plus root 3 by 2 by L. In which sense? In this sense. Because when you stand here, the rod rotates in this way. When you stand here, the rod rotates in this way. Is omega 1 to omega 2 1. Both are equal. Omega 1 2 is equal to omega 2 1. That's the omega of the rod. So rod rotates in this way with this angular velocity. So angular velocity of the rod is this much. Answer. In which sense? In clockwise sense. In clockwise sense. 2 rotates in clockwise sense with respect to 1. 1 rotates, 2 revolves in clockwise sense or turns in clockwise sense with respect to 1, and 2 revolves or turns with respect to 1 in clockwise sense with same angular speed, and the angular velocity of the rod is that. Using this concept of relative angular velocity, let us solve this problem. What is solved by using the ground frame method. When the rod slides with velocity v, length of the rod is L, and this angle is theta. Now we need to calculate the angular velocity of the rod. Let it be omega. The rod, this point moves in this way with velocity let it be v dash, because it is constrained to move along the vertical way or down. This rod, this point of the rod is moving along the horizontal. This v dash, this is v. V is given. We take the velocity component along the rod. Since the rod is rigid, these two velocities will be equal. That is the basic definition of rigid body. If this is theta, this is v dash cos theta, and if it is v, this is v sin theta. The perpendicular component will be v dash sin theta. Here the perpendicular component will be v cos theta. No relative velocity along this direction. There is a relative velocity along this direction. Therefore, angular velocity of the rod is equal to v12 by L or v12 perpendicular by L, because there is no relative velocity along the rod or parallel to the rod. Well, so v12 will be equal to, if we take it positive direction, this will be negative direction. Okay. We can write v1 perpendicular minus v2 perpendicular by L. v1 perpendicular is v cos theta plus v2 perpendicular is minus v dash sin theta by L. This is equal to v cos theta plus v dash sin theta by L. But we do not know v dash. This can be calculated by equating the velocity along the rod or equating the relative velocity to 0 along the rod, or parallel component of the relative velocity of 1 with respect to 2 is 0. So v dash cos theta can be equated with v sin theta. So v dash is equal to v sin theta by cos theta. This is equation number 1, this is equation number 2. Now substitute v dash from equation 1 in equation 2 to obtain, using these two equations, we can find omega is equal to v cos theta plus, instead of v dash you can write v sin theta by cos theta, that is v dash into sin theta by L. So you are getting v, take common cos square theta plus sin square theta by L cos theta, and this quantity is 1. So ultimately we are getting V upon L cos theta, answer. And of course, when you take the rod in this way, this hand is moving in this way, this hand is moving in this way, normal to the rod. Therefore, if you stand here, you can see that this hand moves faster. Or if you stand here, you can see that this way moves faster. In both the ways, you can say that the rod is rotating in which sense? In anticlockwise sense. And you have got the exactly same answer by using the ground frame method. So in both the methods, we can define the angular velocity, and problems also you can solve by using both the methods with equal ease. Regarding the relative angular velocity, I would like to solve a couple of more problems. This is a disk, or this is a circle. This particle is revolving in a circle of radius r. Angular velocity of this particle P with respect to O is omega. Then find the angular velocity of the point P with respect to any peripheral point, let it be Q. That's a conceptual question to brush up the idea of relative angular velocity. This is a circle, not a disk. No connection between these 2 points, no connection between these 2 points, no connection between these 2 points. To solve the problem, we have 2 different methods. One ground frame method, one relative motion method. Let us solve it by ground frame method. For this, redraw the circle. Take these points in this way. This is central point, center of the circle, that is O. This point P, and you can call it Q. If this is theta, this is phi. Or if you want, you can call it P, you can call it Q. Angular velocity P with respect to O, that is omega PO. In ground frame method is given as the rate of change of which angle? This angle. Made with respect to this fixed line, horizontal line, or horizontal diameter, that is theta. This straight line makes an angle theta with respect to the positive x direction or axis. This angle changes at what rate? That is the angular velocity of P with respect to O. Whereas the angular velocity of Q, the angular velocity of P with respect to O, that is given as omega, is given. We need to calculate the angular velocity of P with respect to Q. So here is the straight line. PQ. The PQ makes an angle phi with respect to the fixed line, fixed or reference line, x-axis. Angular velocity of P with respect to Q is given as the rate of change of this angle with respect to time. This is question number 2. By simple geometry, we understand that theta is equal to 2 phi. If you differentiate both sides with respect to time, once we get d theta by dt is equal to twice of d phi by dt. But d theta by dt is defined as the angular velocity of P with respect to O, and d phi by dt is defined as angular velocity of P with respect to Q. So angular velocity of P with respect to O is equal to twice of the angular velocity of P with respect to Q. If angular velocity of P with respect to O is given as omega, angular velocity of P with respect to Q can be written as omega by 2. That's the answer. That's the ground frame method. Let us solve the same problem by using the relative motion method. This problem has nothing to do with rigid body. We are strengthening, emphasizing the concepts of angular velocity relative angular velocity, because this will form the basis of understanding of the rotational kinematics.